Thank you, Nitzan. I'm very happy to be here today. My name is Chen Amiraz. I'm a PhD student in my last year at Weizmann. Today we're going to learn how 1,000 little failures can turn into success. I know this title may send you in some different directions, but I promise you it will all become clear in the next 10 minutes. Here is my thing. Okay. So at this very moment, an abundance of data is being processed by distributed learning algorithms. One example, which many of you may have encountered on the way here, are routing applications like Waze, where each user has their own local view of the traffic, and they send it to the application servers, which then aggregate this data and send back an optimized route for each user. A completely different example is a data scientist studying a disease using electronic medical records that are spread out across different hospitals or HMOs like Clalit or Maccabi. While these problems are very different, they can both be modeled in the same way by a network of many, many machines that are all connected to a fusion center. Each machine sees a different sample of the data, and the goal of the fusion center is to jointly learn from these samples. So what are the challenges in distributed learning? One major challenge is communication constraints, since of the vast nature of the data. And another main challenge is privacy concerns. In my PhD, I studied distributed learning algorithms, which provably overcome both these challenges. So they're both communication efficient and private. Now let's do a short experiment together. This is a noisy image. What do you see? I'm going to give you 3 options, so please raise your hand for what you think is happening here. So it's either A, a gray squirrel, B, a baby elephant, or C, a koala bear. So who thinks it's A? Okay, not many of you. Who thinks it's B? Okay, maybe 10%. Who thinks it's C? Wow, okay, very nice. So what happens if I give you another noisy sample of the same image? So this is a different instantiation of the noise. Does this help you? So many of you will probably say, of course, we can take these 2 images and average them together. So this is like averaging over data given from 2 different machines. And you can do it over 4 machines, or 16 machines, or 100 machines. And at some point, you'd realize that, yes, this is indeed C, a koala bear. So due to noise, it's hard to recover this image individually. So if each copy of this image would be a single sample. But if we communicate and work together, we have a better chance. And as you saw, some of you had a problem seeing this immediately. And if we had more noise, probably many of you would have a problem seeing this immediately. But doing this together helps. And now we're connecting back to the title, where even if a lot of the machines would fail to see what's in the image, actually working together would help do it better. So let's look at our challenges again. So like I said, each machine sees a different sample of the image. And the goal is to output a reconstructed image. So we don't have labels like we had in our example, that was just to get the point across. So if we were to send the images themselves to be averaged, then the total communication would be very high. It would be the signal length, which is the number of pixels in the image, times all the number of machines. And this can be a really high number. And also in terms of privacy, we have to send the signals themselves to be averaged. So this is not private. Solution for this problem, possible solution, is to use voting schemes like we did in our experiment. So basically, if each machine only sent its vote, then we would have a much lower total communication cost. In this talk, we will see that it will even be smaller than the signal length. So it's even going to be smaller than sending 1 copy of such an image from 1 machine. And because we only send votes, then you can feel intuitively this is going to be more private as well. Okay, so why can we save communication? So we're going to use sparsity, which is basically a signal representation which has very few non-zero values. So as many of you know, schemes like JPEG use sparsity. So for example, this picture of the dog up there is not compressed, and this picture down here is compressed using only 1% of the values in the image. So we can really save a lot by compression because of the sparse nature of natural images. This is also true for audio and video signals, for example. So the main idea is we can save communication using sparsity. Now I'm going to formulate this problem more formally. So basically we have a signal which is composed of an unknown sparse vector plus noise. So in this example, the white areas here are zeros and the green areas are non-zeros. And we're going to call these the K support indices. So K is the number of support indices, and the support is what we're going to try to recover, plus noise. And think of the noise as Gaussian noise, but we have also results for different types of noise. Given the support, we can recover the signal itself if we were to send the values. So if we knew it, we just say to each of the machines, just send me the values on the support. But in general, the support is unknown in advance. So, and due to noise, each machine can't find the support on its own because it basically sees values all over the vector. So to conclude what we want to do, each machine gets the same sparse vector, but a different realization of the noise, so it sees a different sample. And our output is going to be the K support indices, so it's the K locations where the vector is not zero. We want the total communication to be smaller than the signal length, and we want it to be private by only sending votes. So what does our algorithm look like? Each machine votes for the K indices with the highest values, and then the center aggregates these votes and returns the K indices with the highest number of votes. So a few things to notice here. First, this algorithm is very simple. I could explain it to you in less than a minute. And it's also pretty simple to implement. It's also fast. These calculations are pretty simple, and it only requires one round of communication. And it's private because it only sends the locations of the non-zero values and not the values themselves. So what we proved here, this is our theoretical guarantee. So on the x-axis, you see the signal to noise ratio. So it's the strength of the signal divided by the noise. And as you go along this axis, the noise becomes smaller compared to the noise. And on the y-axis, you see the number of machines. So in this red area, you would fail even if you had infinite communication because the noise is simply too high. In this green area, even a single machine can succeed with high probability because the signal is really strong. And what we proved is that our algorithms succeed with high probability in a large range of SNR values, and the total communication is smaller than the signal length. So this is a short simulation. We have 1,000 machines. The length of the vector is 5,000, and we have only one non-zero value of the vector that we'd like to recover. In our simulation, the support index is 400. And what you see here is the index from 1 to 5,000 versus the number of votes that it received. So for example, index 1100 got 0 votes, index 2900 got 1 vote, index 21,022 got 3 votes, and our support index 400 got 5 votes. So on the one hand, it got more votes than everyone else because every other index got at most 3 votes. But on the other hand, out of 1,000 machines, only 5 machines selected the correct index. So while 99.5% of the machines fail, our algorithm still succeeds. In terms of communication, the naive algorithm we showed in the beginning that sends everything uses 5 million values. Even sending one image requires sending 5,000 values. But our algorithm can succeed by only sending 1,000 indices. And this is only 0.02% of the naive solution. To conclude, exploiting very small advantages enables success on extremely noisy signals. Or in other words, sometimes you don't have to look for Gulliver in the land of Lilliput. It is enough to simply look for the Taurus Lilliputian. So thank you very much. This is our paper. If you'd like to read more, this is joint work with my advisors, Robi Krautgamer and Boaz Nadler. And feel free to contact me on LinkedIn or email. I'm graduating from my PhD soon. And thank you very much for your attention.